simplest bound state problem, which is this infinite square well. And now I will examine the simplest scattering solutions beyond plane waves. And the problem is the problem of step function. Okay, so something that is 0 to minus infinity, and then it becomes something like this, and then it becomes flat again. Now, any real step is of this form, so it's not a very sharp object, but in order to simplify my treatment, I will make it an actual sharp step like this. Okay? So this is my function. So the potential V of x. This is x. This is 0. And the potential is 0 here. And then it jumps to a value that I will call V0. Okay? What is the minimum of this potential? 0. So I will not look for energies that are less than 0. Positive. Do you expect to find bound states here? Can you bound states with flat potentials? No. Right? Not in this case. Because there is nothing here that forbids this particle from flying to minus infinity. But also you notice immediately that if the energy is in this region, then the particle cannot go to plus infinity, but it can fly away only from minus infinity. On the contrary, if the energy is in this infinite region, so for E greater than V0, the particle is free to escape in both directions. Okay? So let me do first this case, and then I will do this later on. So I will consider the case where E is greater than V0, and I would like to write a candidate wave functions and then try to find the solutions, in fact, by imposing that phi of f is continuous and phi prime of x is continuous. Okay? This is the typical trick we will play in all cases where you have several flat potentials joined together at discontinuity points. Okay? I try to write the functions in every region, and then I join them together by imposing these conditions. 2 at each point. Continuity of the function and of the derivative. Okay, let's start from the simple case. So I have some energy here, E, and I want a wave function here to the left. What would you propose? A free particle, right? So I propose that there I have e to the ikx, right? In that region. So this is again the region x less or equal to 0. That's it. E to the ikx with some positive k, for instance.
No, because it cannot.
You can also have e to the minus kx, right? So let me just superimpose the 2, but in principle here I do not have to assume that the 2 are just with the same weight, right? Why? I mean, in fact I could put here a constant and here another constant. I will argue in a second why I just use one constant and then put this 2 1. Okay? You will see in a second. So these 2 waves are okay. Each one of them is an eigenstate with which energy? What is the energy E that you associate to this or to that? Huh? Yeah, so obviously I want that, but the E, the EK is h bar squared a squared over 2m, and I want this to be greater than V0. Okay, so the K is sufficiently large that okay? Good. What about the wave functions here? Again, the energy is greater than the value there, but now the values are not 0. So do you know how to write a wave function for this right-hand part of the problem? So x greater to equal to 0 is a free particle again. How should I write it? Suggest. e to the I,
That's it.
okay? Okay?
Some new variable.
A new variable or k? That's the precise. If I put here kx, okay? What would be the energy associated to this object here?
It's what you said.
H bar k squared okay, plus v0. So it cannot be the same E.
Yeah.
So I shouldn't use the same K. I should use a different, let me call it Q. And the condition is that H bar squared, Q squared over 2M, which is the piece of kinetic energy associated to this, plus V0, exactly matches the EK I have selected there, which is H bar squared, K squared over 2M. So you see, this gives me a relationship between Q and K, which are not the same, because here there is a V0. Okay. But now, why should I use here the 1? No, I should put some constant. Let me call it Tk. And in principle, you might say, hey, but why don't you put here something like e to the minus qx with some other constant, okay? No, I don't. Okay? I will select my wave function of this form with two constants only. And in this deliberately unsymmetric fashion, here there is a 1, here there is a missing piece. Okay? These are called scattering solutions, and I will try to illustrate to you what is the idea behind. The idea is a preparation experiment. You send a wave with amplitude 1 towards the positive direction. So here K I assume to be positive. K positive. And this wave has a current associated to it. Calculate the current of a wave like this. You will see that is H bar K over M. So it's a positive current of probability density, which travels from minus infinity towards the obstacle. Then the wave is in fact partially reflected. So this is called the reflection coefficient, amplitude. And it goes back again, reflected from the origin. So if you send a wave like this, part of the wave comes back with a certain coefficient. Part of the wave is transmitted, okay, with a transmission coefficient. But there is no wave that actually returns from plus infinity, because you just prepare it from minus infinity, okay? So you can transmit waves, but nothing comes back from plus infinity. Now, you might say, well, but wait, this is only one possibility. What about doing exactly the opposite experiment? You can do that. So you can prepare waves from plus infinity, sent to the thing, partially reflected, and partially transmitted there. Not only that, if I have a certain energy E, I can have two degenerate solutions with the same energy. This we have already seen in the case of plane waves. E to the ikx and e to the minus ikx. They are both solutions with the same energy. Remember the parabola dispersion? There it is. K. This is Ek equal to h bar squared k squared over 2m. You see a positive value and the corresponding negative value have the same energy. Okay? Therefore, two waves, one running positive and one running negative, are degenerate. Okay? So, to make the story a bit short, let me just comment on this fact. Suppose that I call this phi of x. Okay? Is one choice of my solutions. Now, suppose that I have determined everything in such a way that minus h bar square over 2m, second derivative of plus vx applied to this phi k of x is equal to this ek phi x. Okay? I've done my exercise. Okay? Suppose I will do it. Now, you might say, wait. But what about phi star? You see, this object is the star of that, okay? Phi star would be a solution of this equation? Of course it is, right? So I can also write this. Why can I do that? Because this is real and this is real. So phi star also satisfies the equation, right? Therefore, and with the same energy. Therefore, I can combine them together and I write A phi k plus B phi k star. This is still a solution with the same EK, right? Can you tell me now the shape of the solution? Well, you see immediately that to the right of this, you get not only this, but you get also the one with the minus, right? And here, you already have both, but the coefficients of both are different from one, okay? So in some sense, true, I'm doing a specific scattering geometry here, but I'm not losing really much. I should always remember that there is another totally degenerate solution that describes the other scattering geometry. I can mix together them, but in some sense, this doesn't add much to the physics of the problem, okay? It simply simplifies my work, because remember, I do have two quantities to determine, and I have two equations to impose. And so I can do it pretty nicely. While, if I write a general solution with A, B, C, and D, I do have four quantities to look for and only two conditions. You might say, hey, but I have also normalization. Okay, three. I still have one freedom. What is the one freedom? The degeneracy, because I can form two of them, okay? So, I am simplifying my work without really losing much, okay? So please accept at least this, at this moment, this as an explanation for this rather strange and asymmetric choice of the parameter, okay? Together with the physics of this scattering preparation. All right, let's proceed. Okay, let's impose that the function is continuous in zero. Continuity, the first. So, the function to the left of the point is this. In zero, it is equal to 1 plus rk times 1, right? Good. To the right, the function is this. In zero, it is equal to pk. Is it clear what I've done? I've imposed continuity in zero. Now I do the derivatives, okay? So do the derivative of this and the derivative of this. The derivative of this, it's simpler, is I tk q times e to the iqx. The derivative of this is, I bring down here ik e to the ikx, and here minus ik. Okay? Is it clear? These are the derivatives. I calculate them in zero, and I impose that they are the same. So on the left I have ik, 1 minus rk, and on the right I have iq pk. Is it clear? These are the two conditions that I have to impose in order for this to be a solution. Okay? Notice that, as I told you here, K and Q are not two different things arbitrarily. So, in some sense, Q is fixed once you select K, right? In fact, you can, okay, you can express everything in terms of the energy. So the energy is the commanding thing. And given the energy, you know that h bar k is equal to square root of 2m times this energy, and h bar q is equal to square root of 2m E minus V0, okay? So you select an energy greater than V0, and automatically you can calculate what is the K and what is the Q, okay? For any energy, by the way. No condition on the energy. Anything you want, you just calculate the K and Q. And there are the K and the Q that appears in your equation, but I still need to find these two quantities. Obviously, they are determined from solving this very simple 2x2 problem, which I can solve immediately. Right? The I here doesn't matter. Okay. So if you solve this, you get what? You get that T K is equal to 2K over K plus Q, and RK is K minus Q, K plus Q. Okay? Try to verify. It's a very simple. By substitution, for instance. Okay? You can put here TK on this side equal to 1 plus RK. Okay? And then you determine, you see you have Q over K, you put the RK on the other side and we get this equation. And then you put it back here and you determine TK. Okay? Is it clear? Good. Well done. Okay? By the way, these are called reflection amplitude. Try to calculate the currents associated to this wave function and to this wave function. Okay? Remember the current has the phi, grad phi, phi star, grad phi star, minus grad phi star rho. Just do it. And you will see that the current involves Tk modulo square and it involves the Rk modulo square. And remember that the current should be constant everywhere because these are eigenstates of the Hamiltonian in a one-dimensional problem. So the divergence of the current should be 0, which means constant current. If you do this type of arguments, you will realize that the current here in the negative region here is equal to h by k over 2m, 1 minus rk squared. Try to calculate it, okay? So if it was not for this, no reflection, the current is h bar k, momentum divided by the mass. Sorry, there's no 2. Okay? But since there is some reflection, the current is reduced because some of the wave is bouncing back with a reflection coefficient. This is called the reflection coefficient. Notice it's the square of the amplitude that matters here. And then the current here on the right is equal to Tk squared times h bar q over m. Okay? So you see it's the momentum which is reduced, q is less than k, divided by the mass, times the transmission amplitude. This is called the transmission coefficient. Now, the fact that the current is conserved everywhere implies that these two quantities are the same. Okay? So there is a relationship between transmission coefficient and reflection coefficient, depending on the two momenta, obviously, which has to be satisfied. They are not arbitrary. In other words, they are strongly related. Okay? Is it clear?
Yes.
Good. Couple of more minutes before we finish.
Sorry,
Yeah.
I don't get the point where you say it's not arbitrary.
The two are related.
Uh-huh.
The two are related, right?
Yes.
So they are not. In fact, probably you might remember that sometimes this quantity is written. So the sum of the reflection coefficient plus the transmission coefficient is 1. Okay? When this would be correct? Suppose that I have a slightly different problem. Okay? So the while, the step lasts for some time, and then it goes to 0 again. Then I should write a function made of 3 pieces: negative x, intermediate x, and x above this threshold here. And in this region, I would write the equation precisely as tk times, this time, suggest e to the I k x. Okay? If the potential here is 0, the momentum that I have to put here is again k, the same object that I have there. So if I do a scattering from a finite step, the wave that I get here has the same momentum as the wave that is incoming here. Not different. But then you realize that the current there is equal to h bar k over m times tk squared. Okay? In this situation, what can you say to me? This object has to be equal to this. Can you conclude something?
They equal to 1.
This you can eliminate. And therefore, 1 minus this is equal to that.
Equal to some.
Okay? You see? So this equation is indeed there sometimes when you bounce from a finite step. What you get back, what you transmit, sum to 1, which is what you send. Okay? You send 1, okay? You reflect r squared, you transmit t squared, the sum of these two things should match. Or one last remark and we finish. How to solve the second case? The second case looks slightly different because here, if the energy is less than V0, the function to the right cannot be a plane wave. What functions would you suggest to me to use in that region?
Decreasing exponential.
A decreasing exponential, precisely so. So this becomes tk e to the minus q times x. Real. Q is now the coefficient of this real decaying exponential. But why did we never consider decreasing or increasing exponential as eigenfunctions of a plane wave so far? This is a plane wave in some sense, or not a plane wave. It's a free particle with some modifications. The energy is less than the 0 of the, so suppose that I consider a free particle. Okay, so the potential is 0. I told you E positive, all right. I can choose this with energies Ek equal to h bar squared, k squared over 2m. We never consider negative energy. But in principle, if I take e to the plus or minus q times x, which is an exponential, then you can calculate, you just put in the Schrödinger equation, and the energy is minus h bar squared, q squared over 2m. Negative, certainly. We never considered that. Why?
It must be.
Let's plot. Let's plot, say, the one with the minus, which is something like this. Okay? So it's 1 here, and then goes to 0. It's not normalizable for sure. But you might object. Yes, you also decide to keep the plane waves that are not normalizable in infinite volume. So why are you making such a difference between non-normalizable functions like this and non-normalizable functions like this? The point is that this function is not only non-normalizable, but it's also physically meaningless, because it tells you that the probability of finding the particle arbitrarily farther away and more negative is bigger and bigger. It makes no sense at all from the point of view of the interpretation of this as solution of the Schrödinger problem. So we never consider this mathematical possibility in our story about free particles. Nevertheless, if this part of the world has a different story, in this positive x region, a decaying exponential makes some sense. Okay, it is normalizable there for sure, and if you bar what happens in the southern region, will make sense. It's an evanescent wave. That's the way it is called. Okay, evanescent. It means that it is a wave that has a tail that goes to zero. So you can, in principle, do that. This is good. It's an evanescent wave. You can calculate what is the energy associated with that, and you write the generalization of this, and you realize that since E is less than V0, you have a square root of a negative thing, which you can write as the positive thing with an extra I there, okay? And with this extra I, indeed, okay, you transform this exponential here into that. So in other words, if instead of using Q, I use IQ, immediately I transform this. So rather than having Q in my equation there, you substitute it with IQ. Okay? So this wave becomes that. This object here becomes immediately a minus, which is the correct thing to have. And all equations are exactly the same. Okay, so you can put here, so I tell you, try to do it, but I tell you the solution. The solution is dramatically simple with this trick. You could redo it again. But if you don't want to redo it, believe me, that what you get is this. Okay? So in the second case, here you get IQ rather than Q. And notice also that this object here is a complex number divided by this complex conjugate. So this is a modulus 1 number. Okay? Modulus 1 suggests that the TK, I shouldn't use this. I should use this. But it suggests that the current here is actually 0. The current here. This is still correct. And modulus R equal to 1 means that the current here is 0. Is the current to the right for a solution like this 0? Yes, because it's a real function. You remember, if you calculate the current of a real function, do the exercise, please. Did you do it?
Yeah, no.
Did you really do it?
Yeah, I remember.
Okay, good. The current of a real function is 0. And therefore, yes, nicely, this is a real function, and the current is 0 here and 0 there, because the reflection coefficient has modulus 1. Okay? That's it. Okay, bye-bye, see you next week. Ciao.